Hey everybody, it's Mr. Farrell here. I just wanted to create a test prep video for the test dealing with waves that we have coming up. Some folks have already taken the test. You can use this video to study for your retake. If you still haven't taken the test yet, then feel free to use this video to study for that. In order to prepare for this test, we're going to be using homework set 5 as our focus. All right. As I mentioned in class, homework set 5 covers everything that would be on the test and that will be on the test. As a matter of fact, it actually covers more than that because on homework set 5, you will also see decibel problems included. That information, those problems will not be on the test because that is going to be covered and has been covered in the project, project that you all are doing with music production. So we're not going to be covering decibels in this review session. Also, if you look at problem 2 on homework set 5, where it asks you to label the wavelength, amplitude, frequency, that is also not going to be on the test because that information is being covered in the project. Okay, so homework set 5 goes above and beyond what is going to be on the test. So certainly if you can do everything in this homework set, then you'll be good to go for the test. All right, so we'll start off at problem 1 on homework set 5. It asks you to please define simple harmonic motion. Now, simple harmonic motion, we've talked about it. We've done some experiments with it. It is that repetitive, constant swinging motion that we see in a pendulum, a grandfather clock, a spring that has a weight on the end of it, right? It's that constant repetitive motion. So if you were to describe simple harmonic motion, you could say it is motion of an object that has a restoring force that's trying to bring it to its equilibrium position. All right, now to break that down into those individual pieces. Now, having a restoring force means that when you go too far to one side, there's a force pulling you back. And then when you go too far the other way, the force is still pulling you back. All right, so a restoring force, we see that in a spring. When we drop it, it stretches and there's a restoring force pulling it back up. We see that in a pendulum. When it goes too far one way, it wants to come back the other way, right? So there is a force that is trying to pull it back to a equilibrium position. It's trying to change its direction, okay? And essentially just pull it to equilibrium, which is the second part of simple harmonic motion. Is the object is trying to get to its equilibrium position, okay? So with a pendulum, the equilibrium is in the middle, and so you'll see that the restoring force changes direction based on which side of equilibrium you're on. If you're on this side, it's pulling you back to the middle this way. If you're on this side, it's pulling you back to the middle that way. So it varies which direction it's pulling you based on what side of equilibrium you're on. So the two key things of simple harmonic motion, there is a restoring force and the force is trying to pull you towards the equilibrium position, okay? Now again, we're gonna skip over question 2 because this video is mostly for test preparation. So you won't need to know that on the test, okay? Same for question 3, actually. You won't need to know question 3 information on the test. That stuff is being covered in your music production project. Now we get to problems 4, 5, 6, and 7, and 8. So problems 4, 5, and 6 cover this equation that I'm gonna write on the board. So frequency times wavelength equals velocity, okay? So frequency times wavelength equals velocity. This is covered in problems 4 through 6. And then we have the equations 1 over frequency equals period, or 1 over period equals frequency. Okay, that looks to be problems 8 and 9. They're dealing with those equations. Okay, Now, I'm actually not gonna cover these equations or walk through these problems with you in this video. And the reason is because there is another video in which I already walk through using this equation and using these equations. So you can find that video, it's on my YouTube page. It's also in the physics help folder. So if you go to the physics help folder and you look for the video on frequency, wavelength, and velocity, you'll find the video that covers this equation. And if you go into the folder and look for frequency and period, you will find the video that deals with these equations, okay? So again, we're not gonna spend this video time going through these equations. Just go to the physics help folder and watch the YouTube videos on these equations to help you prepare for that on the test. All right. So moving on to problems 9 and 10. So problems 9 and 10 are asking us about longitudinal versus transverse waves, okay? A good way to think about it is a longitudinal wave goes back and forth like this, okay? So you'll notice that the way I'm pushing my arm, the way that I'm vibrating is the way that I'm moving, right? So my arm is pushing this way, it's pushing back and forth, and the vibration of the wave is going to go back and forth, okay? You can think of, so that's a longitudinal wave. You can think of transverse waves as going like this, right, with your arms. So if you notice, I move my arm up and down. That's how I create the motion. My hand goes up and then it goes down. But if you look, it looks like the wave moves across the screen this way. So the direction of my vibration, which is up and down, is perpendicular to the direction that the wave is actually moving, which is this way, right? I go up and down, but the wave travels across the screen, okay? So we can represent that, starting with problem 9, by showing, so this is asking about a longitudinal wave. So problem 9 says, is a longitudinal wave parallel or perpendicular? All right, so let's go ahead. All right, I had a little brief call there on my phone. Let me make sure this was recorded. So we're gonna start with problem 9. Problem 9 asks, for a longitudinal wave, are the oscillations perpendicular or parallel to the motion of the wave? Now, again, longitudinal waves are waves where we push things like this, okay? So if you look, I'm pushing parallel to the way that I'm moving. So if I push to the left, I'm actually moving to the left. If I push to the right, I'm moving to the right. And so my vibration and the direction of motion are the same, all right? And because they're the same, they're parallel to each other. So you could say parallel, or you could write them like this. So I'm going to do both. I'm going to say parallel, and then I'm going to draw a parallel side-to-side arrow that says motion and vibration. Okay? So again, the motion of my wave is actually side to side, and the vibration, the way I'm pushing it, is also side to side. So they are parallel, right? Now for problem 10, it's asking about a transverse wave. Now again, we know that a transverse wave, I'm lifting my hand up, but the wave is traveling across the screen, okay? So I'm moving my hand up, but the wave goes this way, okay? So for a transverse wave, they are perpendicular to each other. So I'm going to draw one arrow this way and one arrow this way. So my vibration is going to be up and down, and my motion is going to be left and right. Okay? So this is perpendicular. Right? Sweet. Okay, so again, with transverse waves, I'm moving my arms up and down, but the wave travels that way across the screen. Okay, so again, the motion of the vibration, me moving it up and down, is different than the direction the wave is moving, which is that way down the screen. Okay, all right. So problems 9 and 10 seem good. Again, we're going to skip over problems 11 through 14 because we are not going to cover decibels on the test. They are being covered in the project. All right. But let's go ahead and jump to problems 15 through 17. Okay. So we're actually going to do problem 17 first, all right? And the reason is because 17 allows us to draw a model, and then we're going to explain that model in problems 15 and 16. So in problem 17, it asks us to draw an example of the Doppler effect, okay? And we've got a person A standing over here and a person B standing over here. So person A is in front of the vehicle, person B is behind the vehicle, okay? Now, the Doppler effect does not impact the amplitude of the sound. That is not what we're talking about when we talk about the Doppler effect. So yes, as an object moves away from you, it will get quieter, right? But that's not the Doppler effect at work. The Doppler effect is when the motion of an object causes the sound waves to bunch up or spread apart. And as you know, if there are a lot of sound waves close together, that means you'll hear a lot of sound waves per second. If there are sound waves that are spread apart, you'll hear less sound waves per second. And sound waves per second is frequency, right? So if we have a lot of sound waves per second bunched together, that means we have a high frequency. If we have fewer sound waves per second because they're spread apart, that means we have a low frequency. That's like a low voice versus a high voice. The loudness of both voices can be the same, but one voice still sounds low, one voice still sounds high, okay? So in this image, we're gonna draw the sound waves in front of let's call this an ambulance. We're gonna draw the sound waves really bunched together, right? Because that ambulance is pushing all of those sound waves together, and that's gonna make it sound like there are more sound waves per second, so it's gonna be a higher pitch. Back here, because the ambulance is moving away, we're gonna get fewer sound waves per second heard by this person in the back. So that means it's gonna sound lower in its pitch. It's gonna sound like a very low sound. Not quiet, but like a deep bass voice versus a high-pitched singing voice, you know? So that's gonna sound like a bass. This is gonna sound like a soprano, right? So higher pitch versus lower pitch, not loudness difference. That's not what we're focused on, all right? So this is what your image should look like for problem 17. A lot of compact, compressed sound waves, and then a lot of sound waves spread far apart, okay? Now we're gonna look at problem 15, which asks us, according to the Doppler effect, the pitch of a sound will get higher or lower when the sound is moving away from you. Now, as we see here, the sound of this ambulance is moving away from person B, and the sound waves spread out more, so this is going to be a lower pitch. Okay, so we've got a low pitch here. So that's a low frequency. Okay, because we have fewer waves per second, right? Looks like in this image we have 2 waves per second, so very low frequency. All right. Now if we look at problem 16, it says as the sound source is moving toward you, is it going to have a lower or higher pitch? So as this ambulance is moving toward us, it's got a lot of sound waves bunched up together, so a lot of sound waves per second. So that's going to be a high pitched sound. So high pitch or high frequency. Okay? Awesome. So low pitch, if the ambulance is moving away from you, which is a low frequency. High pitch or a high frequency if the ambulance is moving towards you. Okay? Awesome. So now we're on the last topics that we're going to cover on this test, and that is superposition. Okay? Now, I'm going to draw just an example of superposition on the board, and then we'll do problems 18 to 19, then we'll go to talk about 20 to wrap up our review session. Okay? So constructive interference. All right, let me write constructive on the board. Constructive interference is when you have two waves that are in phase, as we call it. To be in phase means that they line up with each other. So I've got a wave up here, and I've got a wave down here. Now, if you look at both of these waves, you'll notice that these waves line up with each other. Okay, so if I made dash marks, their crests line up, their troughs, right, the bottom part of the wave line up, all the way down this way. Okay, so if the crest and if two crests line up, that means when these waves are added together and combined, they're going to make an even bigger crest. Okay, very large. Now, because these troughs line up, they're going to make a very big trough, so very low. And it's going to keep repeating, very high, very low, very high. Okay, so superposition is simply when we combine waves. All right, now constructive interference is when we combine waves and they add together to make a bigger wave. Okay, so this is superposition, but it is constructive interference because these waves lined up to make a bigger wave. Because the two crests make a bigger crest, two troughs make a bigger trough, again, two crests, bigger crest, and so on and so forth. Okay? All right. Now we're going to do destructive interference. Again, destructive interference is still superposition, but it is superposition that is destructive, okay, to the waves. So destructive. Okay, now let's go ahead and draw our waves again. So this is our first wave. And then let's go ahead and draw a second wave. All right, now in destructive interference, one of the first things you'll notice is that our crests and our troughs do not line up. Okay, in fact, in this example, they are opposite each other. So when we have crests and troughs that are opposite each other, they cancel out in a way. And instead of making a bigger wave, they make a smaller wave. Okay, because this wave's trying to go up, this wave's trying to go down, they end up canceling each other out, and so we end up just getting a very small wave. Now, it's not that the wave completely disappears, right? But these two waves combining together will make a smaller wave, okay, in this case. All right. Now, one thing that I do want to note before moving on is that sometimes in constructive interference, you'll have constructive or destructive. Let's go ahead and do constructive real quick. Okay. So I'm just going to put CON so we know it's constructive interference here. Sometimes in constructive interference, you'll have a wave like that, and then you'll have another wave that's very small, that's being added to it. Now, you might ask yourself, is this constructive interference because this wave's very big and this wave is very small? Well, that actually doesn't matter. It's still constructive interference because these waves line up, okay? My crests line up, my troughs line up, my crests line up, my troughs line up. This one's a little off. Let me line that up a bit more. All right. So as you see, even if one wave is bigger or has a larger amplitude than another wave, as long as they line up with each other, they're going to combine to make a bigger wave. Now, this can happen with destructive interference too. One wave can be bigger, the other wave is smaller, but again, if they are out of phase, if they don't line up with each other, regardless of how big one is over the other, if they are not lined up, they're going to cancel each other out and make a smaller wave, okay? Sweet. So now let's go ahead and talk about problem 20. That is the last problem for our review. It says, explain how superposition allows instruments and human voices to have different timbre. You can use drawings and models to help you. Now, when you think about timbre, remember it is when we have different frequencies produced by the same instrument, okay? Or the human voice, right? We speak and our voice sounds unique because we are playing multiple frequencies at the same time. Now, if we were to look at a trumpet, let's make a little trumpet here real quick. All right, so if we were to listen to a trumpet make sound, it'll have a spectrum that has maybe a high wave at this frequency, high amplitude at this frequency, all right? And maybe, let's do some high amplitudes over here as well, okay? So this frequency, and this frequency are all different frequencies, but the trumpet is playing all of them. Just for the sake of keeping track, let's label them 1, 2, 3, and 4. Okay, so this trumpet is playing all of these 4 frequencies. Now, if we were to pick up a guitar, all right, there's a guitar for us. Okay, if we were to pick up a guitar might sound more high at this frequency and this frequency, but a little lower at these 2 frequencies, okay? So again, the trumpet and the guitar are playing the same frequencies, but the guitar plays these 2 loud and these 2 soft. The trumpet plays this one soft and all 3 of these ones loud, okay? But how is it that they're all playing the same frequency, but they sound different? That's where timbre and superposition come into play. Now, superposition allows the trumpet to combine all these frequencies to make its unique sound. Superposition allows the guitar to combine all these frequencies to make its unique sound. Without superposition, we wouldn't necessarily hear the trumpet's unique voice. It might be the case that only the loudest sound is the one that we would hear, all right? With a guitar, if superposition weren't true, then we might not even hear these lower frequencies, we might just hear the loudest one, okay? And so because of superposition, we're able to hear even the lower frequencies that the guitar makes in order to give it its unique color, its unique sound. All right, so when we think about what is the connection between superposition and timbre, it is that superposition allows timbre to happen. And the way it allows timbre to happen is that superposition combines all the different frequencies that an instrument or a human voice makes. It takes all those different frequencies and combines them to make a unique sound, okay? So that is how superposition and timbre relate to each other, and how superposition actually allows for timbre to happen. Okay, so when we talk about it on the test, I want you to really articulate not just the fact that superposition makes timbre happen. I want you to articulate that superposition combines all the different frequencies produced by an instrument or a person's voice, and it combines those frequencies to make the unique sound of the instrument or their voice, okay? All right, thank you. So I hope this was helpful. I'm going to post this on YouTube, obviously, because that's where you're watching it right now. But have a good one. Come talk to me during tutoring time or anything else if you need extra help.